Hi everyone, welcome on board. Welcome all to the presentation of the Internship B4 cohort presentation covering all aspects of the internship and project undertaken for the online training about embedded systems. So let us begin with the following presentation from the beginning. So my name is Nasr Mohammed Abdallah, pursuing mechanical engineering at the University of Nairobi here in Kenya. So among the topics that were covered during the online internship were introduction to embedded systems and microcontroller. We had the C programming language, and then we also underwent the PICSIM lab microcontroller, specifically the PIC16F877A. We also looked at the microcontroller architecture, specifically on the datasheets. Also, we looked into how we can program the microcontroller. We looked also at peripheral interfacing, communication protocols, and lastly, we are going to look at the car black blocks project. So what are embedded systems? Embedded systems, these are specialized computing systems with chip-enabled hardware and software, which specifically perform a specific task or application. Among its benefits that it has low power consumption, low cost, and high performance. Its demands is that it must respond quickly to sequences and combination of events, perform multiple separate activities simultaneously, handle faults without crashing. What are some of the applications of the embedded systems? We have the home appliances such as the washing machine, the microwave, oven, air conditioner, etc. Also, we have the health and fitness appliances such as the smartwatches and the wristbands. Also, we can use embedded systems in automobiles such as cars and bikes. Also, you can use embedded systems in traffic monitoring, smart parking systems, and also usually used in the Alexa. So what are some of the types of embedded systems? We have two categories of embedded system, which stands for simple embedded systems, whereby for the simple embedded system, these are non-operating system-based applications, such as the digital clock, the temperature monitor, and also the smart fridges. While for the complex embedded systems, which requires an operating system, these include such as the Missile, the Alexa, and the network routers. Whereby we can also classify the types of embedded systems as standalone, real-time embedded systems, networked embedded systems, mobile, and hybrid embedded systems. And what are some of the major components that are usually required for the embedded systems to function? One is the microcontroller / the microprocessor. Two is the memory, whereby the volatile memory that can store the commands that are being required, specifically stored in the RAM. Next, we have the storage, which stands for the ROM and the flash, whereby we can store our program. Next, we have the input and output peripherals, such as the keypad, the LCD, the sensors, and so many other peripherals that are required for the embedded system to function. And lastly, we have the FPGA, which stands for Field Programmable Gate Array. Hence, let's dive deeper and understand how the embedded system works. So the principle of operation for the embedded system is that, one, we have to store the instruction. So from the memory interface, we have to fetch the instruction. And then after fetching the instruction, we need to decode the instruction. And then that instruction which has been decoded need to be stored in the register banks. And then from the register banks, it can be taken to the microprocessor, which stands for ALU, Arithmetic Logic Unit, whereby it processes the command and then takes it back to the memory interface again, or taking it to the output required, like the actuators, which can perform that command and task. So as you can see in the diagram, we have the sensors which generates that information, and then it is stored either in the memory, or from the memory it's going to submit that instruction. And then from the memory it's being decoded and then taken through the register banks and then taken to the CPU, whereby the CPU is going to analyze the instruction and then it's going to submit it to the device that is required, to the actuator, to the relays that are going to drive that instruction. Okay, that was about the embedded system programming. Then, before we design the embedded systems, we need to understand the language that can be used to program the embedded systems, and that is the C programming language. So during the internship program, we were able to undergo the C programming language, whereby C programming language is a general purpose programming language with free formatting format, which is efficient, portable, and plenty of library of facilities. With the C programming language is commonly used in system software development, embedded software development, OS kernel development, firmware, middleware, and driver development. Also can be used in the file system development. So among the categories that are being usually referred when understanding the C programming languages are the data type, whereby the data type refers to the character, the integer, the float, and the double. Also, we have the modifiers such as the signed, unsigned, and the short, and the long. Also, we have the qualifiers, which stands for constant, volatile. We have the loops, whereby we can use the loops to reiterate the action or the command that we want, whereby for the loops, which stands for the for loop, the while loop, and the do loop. And then also we can program some decisions that the instruction is going to be looked into if it meets the standard criteria. So with the decision in the C programming language, we are using if statement, else statement, switch, and the case statement. And then you have the jump, whereby we have the go to, the break, and the continue. And then you have so many others categories such as the void, return, and the size of, which can be used to calculate the size of the string, of the character, and many other things. So among the applications that I use in concurrent with the C programming language, we had the dev C++, and also we had the online GDP, whereby it was an online compiler that is being used to run the C programming language. So below is a sample of the C code, whereby the above code, always we need to declare with the main function. So we have the int main, and then we need to declare the variables, whereby we have the int y, we have the int x, and then from the int y and int x, we have the x declared with a variable of 0. And then we have the instruction y is equal to x plus plus, whereby this stands for y is going to have the same value as x, but x is going to increment by 1. Hence, therefore, when we are going to print the result using the C programming language, we are going to say printf, open the bracket, and then use the commands that we normally use in the C programming language. And thereby, our output from this programming language, from this code that we have designed, is that our answer is going to be x is equal to 1, and then y is equal to 0. Among other concepts that are understood in the C language are the data types, the conditional constructs, the operators, the ternary operators, and many others. And then we have the arrays, the pointers, functions, qualifiers, and strings. So that was about C programming language. Then we went ahead and looked at how we can integrate the C programming language with the embedded system. So we had to download some of the softwares. And among these softwares, we have the MPLAB X IDE, which is a development environment which can use to program using the C programming language to design our embedded system. And therefore, we also need a compiler that can cross-check the program that we had written using the C programming language. So we have the XC8 compiler that is integrated into the MPLAB X IDE development environment. And then lastly, we need to simulate and see if our code is actually running. So we are using the PixSimLab simulating tool to simulate how actually our program or our microcontroller is going to function when we install it into the embedded system. So among the interfaces, as we can see, we have the MPLAB X IDE. And also on our right, we have the PixSimLab tool that we can actually use and operate. So from the PixSimLab, as you can see, we have so many peripherals embedded into it. So we have the PixSim microcontroller. Here it is. And then you have the LCD, we have the fan, we have the 7-segment display, we have the digital pads, we have the LEDs, we have the potentiometer, we have the RTC, the real-time clock, we have the EEPROM, and so many other peripherals that are being utilized in the PixSimLab environment. So let's dive deeper into what is this PIC microcontroller, specifically the PIC16F877A microcontroller. So this is a 40-pin microcontroller, whereby it's a peripheral interface microcontroller controlled by a software and programmed in such a way that it performs different tasks and controls the generation line. Also, it is based on the RISC architecture and have two separate memories, whereby the memories we have the program and the data memory, each with separate buses. As we refer to buses as pathways that information is being relayed. So for the program memory, this stores the program code and is accessed by the program counter register that holds the address of the program memory. So the address 000H is used as reset memory space, while 0004H is used as an interrupt memory space. And the other type of memory in the PIC microcontroller, we have the data memory, which this consists of the EEPROM, the E double PROM, and the RAM with multiple banks referring to the general purpose registers and special function registers, which can be used to control different operations of the chip resources, such as the timers, the ADC, the analog to digital converter, the serial, and the input and output ports, among many others. So in the PIC sim lab, we have the microcontroller, which is the PIC16877A. And in them, we have two types of memory, the program memory and the data memory. So in the program memory, this is where the program is being stored. While in the data memory, this consists of the EEPROM and the RAM, whereby it has multiple banks that control the general purpose registers and also the special function registers. So also the PIC microcontroller, it's consisting of 5 ports. So from these ports, we have port A, port B, port C, port D, and port E. It is from these ports that we can use to allocate our instruction, whereby in it, they have different characteristics. So for example, port A, it is a 16-bit port, which can be used as an input or an output port based on the status of the tracer register. Also, we can use port B, which is an 8-bit port, which can be used as both an input and an output, whereby 4 of its bits, when used as an input, can be changed upon interrupt signals. Port C is an 8-bit port, also same as port B, whose operation, whereby the input or output, is determined by the status of the TRISC register. And also we have port D, which is also an 8-bit port, which apart from being an I/O port, it also acts as a slave port, as we are going to see in the communication protocols, for connections to the microprocessor bus. And lastly, we have the port E, which it is a 3-bit port that serves the additional function of the control signals to the analog to digital converter. So what are some of the peripherals that are attached to the microcontroller? We have the LEDs, excuse me, we have the digital pad, the timers, the interrupts, the double EEPROM, the RTC, which stands for real-time clock, the CLCD, which stands for character liquid crystal display, the ADC, the analog to digital converter, and also we have the potentiometer. So we looked in the internship program, we looked at the digital keypad, whereby we specifically refer to the tactical switches. Whereby the tactical switches, we had the pull up and the pull down tactical switches. Also, we looked into the bouncing effect of the tactical switches. And also we looked at the level triggering methods that are used in using the tactical switches. We also went ahead and looked at interrupts. We really dived deeper into understanding the interrupts. And we found that interrupts, these are a process of creating a temporary hold to the main program and pass the control to external sources and execute their task, and then passes the control back to the main program where it had left off. So an interrupt simply is like a hold to the main program. So you have your code running in the microcontroller, but you do a temporary hold to the main program. And then you give the external sources to execute their task, and then they return back to the main program where it had initially left off. So the interrupt flow is that one, the internal or external device requests the microprocessor to stop the processing. So it stops the program from the microcontroller. And then the microcontroller acknowledges the request. And then it attends to the request from the interrupt. And then it goes back to where it was interrupted. So for this to happen, we have the interrupt handlers, whereby we have two categories of interrupt handler. We have the IVT and the ISR, whereby IVT stands for interrupt vector table, which checks for the interrupt address and executes is the ISR subroutine. While for the ISR, which stands for interrupt service routine, it checks for the interrupts and attends to the request of an interrupting source and must be terminated by the rectifier. So the most interrupt handler that is currently used is the ISR. It checks for the interrupts, and then it attends to the request of that interrupting source, and then it is terminated by the rectifier. So we have an interrupt. So it has to be acknowledged by the microcontroller. So the microcontroller has to stop the processing, acknowledges the interrupt, and then attends to the request, and then after the interrupt is being done or completed, it returns back to the initial program where it had left off. So there are 15 sources of interrupts, both hardware and software. And these interrupts record individual interrupts in each flag bits. So when interrupt occurs, the microprocessor completes the instruction being executed, disables the global interrupt enable, the GIE, which makes it to 0. And then it places the address from the program counter to the stack. What are some of the ISR requirements? The service routine. Excuse me. So among the requirements is that it needs to be kept simple and short. And also, for the interrupt to work efficiently, we should not use the block statement, such as the for and the while loops. So let's dive deeper into some of the interrupt terminologies. So interrupt latency. So this refers to the time when the interrupt occurs to the execution of its first instruction. So it is the time period when the interrupt occurs until the execution of its first instruction. So this can be determined by the instruction time, how much content need to be saved and restored, the effort to implement priority scheme, and also the time spent on executing the protected code. In the next peripheral, we looked at the timers, which also play an important part in the embedded systems, especially the microcontroller. So for the timers, these are used to measure the running time or generate accurate time delays. Simply, they are binary counters that can be configured to count clock passes. So once it reaches the maximum value of 255, it will roll back to 0, setting up an overflow flag and generates the interrupt if enabled. So timers, simply these are used to measure the running time or to measure the count to the clock pulses. And then when it reaches the 255 for the 8-bit, it will roll back to 0 and then execute that interrupt if there is any. So in the microcontroller, the PIC 16877A, we have 3 timers, whereby we have timer 0 and timer 2, which are 8-bit timer, where they can also be used as counters. And then they have the 8-bit prescaler. While for the timer 1 is a 16-bit and can be incremented during sleep via external crystal clock. The following is a summary of some of the timers. So as we can see, timer 0 and timer 2 are 8-bit, while timer 1 is 16-bit. And what are some of the control registers used in those timers? We have the option reg, whereby for the option reg in timer 0, we configure the timer 0, the prescaler, the clock source, and many other peripherals. And then for the control register timer 1, we have the T1 con, while for the timer 2, we use the T2 con control register. While for the count register, we have the timer 0, which holds the timer count value, timer 1H, timer 1L, and for the timer 2, we have timer 2 count register. And then what happens to the interrupt on overflow? So in timer 0, we have FFH to 00H, and then you have for timer 1, quadruple FH to 00H, and then for the timer 2, which also looks similar to timer 0 for the 8-bit, which is FFH to 00H. So what are some of the terminologies used in timer? Just like we saw with the interrupt, we have latency. So in timer, we have several terminologies that we really need to understand for us to make use of the timer, to use them as counters in our programs. So one of the terminology is the resolution. What is resolution? This refers to the width of the time register, whereby it refers to 8-bit, 16-bit, and so forth. But with the width of the time register, this refers to the amount of data that it can hold, or the amount of data that it can count from. So it can start from 0 to 255 for the 8-bit. If it's for the 16-bit, it has to be 16 by 2 to the power of 2 to get that amount of values, which can stand to almost 16,000 and something. But for the 8-bit, it counts from 0 to 255. The next term we have the tick, whereby for the tick, we have the up count or the down count. This refers to the methodology in which the timer can count from. It can count from the up count from 0 to 255 or down count from 255 to 0. Next terminology, we have the quantum, which refers to the measure of time responsible for a tick, which is usually based on the system clock settings. But the system clock settings depend, but we usually use the 20 millihertz. But it refers to the measure of time responsible for the tick. 1, 2, 3. So all those are ticks. So how does it move from 1 to 2? That is the measure of time referred to as quantum, based on the system clock settings. Next terminology, we have the scale. So this refers to the method where we can delay the process of going into the interrupt service routine if required. So for the interrupt to occur, just like we saw, we can scale it and delay the process of going into the interrupt. So we can use the scale. So in the scale, we have the pre-scale and also we have the post-scale. For the pre-scale, this is based on the instruction cycle, while for the post-scale, this is based on the overflows. So some of the formulas that are being used to calculate for the timer 0 and timer 2 as the following we can see. We have for the delay, we have the formula is equal to 256 times the prescaler, which is the 8-bit if it's 16-bit, and then times 4 over the frequency of the scale. And then for the reg value is equal to 256 minus the delay, the value that we had obtained above, times the FOSC divided by the prescaler times 4. So what are some of the steps in configuring and using the timer 1 for delay generation? So 1, we need to calculate the timer count for the required delay. So if you want 1 second delay, we need to calculate the timer count for the required delay. And then we need to set the prescaler bits in T1 con, the control register, as we had seen earlier, as per the delay calculations. And then we need to select the clock source, the internal or external, using the timer 1 CS bit. This is for timer 1. Remember, we have timer 0 and timer 2, which are 8-bit. But for timer 1, this is 16-bit. So it has an additional process or an additional step, which is step 3 for timer 1, whereby we need to select the clock source or the internal external using the timer 1 CS bit. Next, we need to load the timer value into the timer 1H and timer 1L register. Also enable the timer 1 interrupt by setting timer IE bit. Also enable the global and the peripheral interrupts by setting GIE and PIE bits. And lastly, finally start the timer by setting the timer 1 on bit. I think that was it about the timers. So let's get to another peripheral, which is the ADC, which refers to the analog to digital converter. So this ADC, it converts analog voltages to a number so that it can be handled by a digital system like the microcontroller. So, for example, this allows the interface to allow all types of analog devices such as temperature, light, touch sensors with the microcontroller unit. We might be experiencing some difference in temperature or intensity of light or a feeling of the touch with the sensors. So these are all analog values, but the microcontroller cannot grasp these analog values. So we need the ADC to transform them into a number that they can be understood by the microcontroller. So the PIC16F microcontroller consists of 8 channels, 10-bit analog to digital converter. The operation of the AD converter is usually controlled by the special function registers, which are 4 of them: the ADCON 0, the ADCON 1, the ADDON, and the ADFM. So the lower bits of the converter are stored in the address cell, 8 bits, and the upper bits are stored in the address register. So it requires an analog reference voltage of 5 volts for its operation. So the disadvantage of the analog to digital converter is that it needs to have a reference voltage of 5 volts so that it can calculate with reference to the 5 volts of its operation. So if it's a value from 0 to 5 volts, it needs to be understood that the analog value will range from 0 to 1023 for the 16-bit, for the 8-bit, sorry. So what are some of the terminologies also referred in the ADC? So we had the resolution. So this resolution specifies exactly how the ADC measures the analog input signals, which also refers to the register width. Also we have the step size, also known as the LSB. This refers to the minimum value change results. Also we have the full scale range, maximum representable amplitude. The channel, this refers to the pin which link external components to the ADC. Acquisition time, the time used to convert to the signal. The sampling rate, this specifies how fast the analog to digital converter can take the readings. That was it about the ADC, the analog to digital converter. So let's now take a deep dive to the CLCD, which stands for Character Liquid Crystal Display, whereby we usually feel happy about the embedded systems when we see the CLCD, because this enables us to interact with the embedded system. So what is this CLCD? It's a 16 by 2 LCD which has two registers, where it has the data register and the command register. So as we had seen earlier, registers, this is where the commands are being fetched or installed. So the RS, the register select, is mainly used to change from one register to another, from the data register or to the command register. So when the register set is 0, then it is known as the command register. And similarly, when the register set is set to 1, then it refers to the data register, where it is going to receive data and showcase it in the LCD. Also, for the command register, it is used to store the instructions of command which are given to the display, such as clearing the display, initializing it, setting the cursor place, and also displaying the control. So for the 16 by 2 LCD, we can command the register to place our cursor at any place we want. Also, we can tell it to clear the screen for us. And also, we can initialize and control the display of our LCD using the command register. While for the data register, it is used to store the information which is used to be exhibited on the LCD screen. So for the data register, simply holds the information, while for the command register, it is used to command how the LCD is going to output our results. Okay, those were some of the peripherals that we discussed in the internship program. And below, we also have another category of information which refers to the communication protocols, whereby communication is simply transfer of information from one place to another. But for the embedded systems to work efficiently, they require the I2C protocols. So what is this I2C? So I2C stands for the Inter-Integrated Circuit. For the I2C protocol, it refers to the transmitting and receiving of information step by step, serially with respect to the clock pulses. Specifically, the half duplex protocol. So we have three modes of communication. We have the full duplex, the half duplex. So for the half duplex protocol is that for communication to happen from one peripheral to another, it needs one to communicate to the other while the other stops the communication. And then when the other wants to communicate to the other, the original or the latter communicator needs to stop and receive the communication from the other party. So the I2C protocol refers to the transmitting and receiving of information step by step, serially with respect to the clock pulses. So for communication, we require two wires, whereby we require the SDA and the SCL, whereby SDA refers to the serial data line, while the SCL refers to the serial clock line, which both of them are bidirectional, whereby they can carry information between devices to the microcontroller. As we had seen in the internship program of how the I2C protocols from the microcontroller to the RTC, the real-time clock, whereby we require the two wires, the serial data line and also the serial clock line. So for the I2C protocols, one is that it is a master to a slave communication protocol, and each slave needs to have a unique address. So the master device, usually the microcontroller, sends the address of the target slave device, either the ADC, the EEPROM, the real-time clock, and any other peripheral, and then reads or writes the flag to that slave. So when the address matches the any slave device that is device is on, the remaining slave devices are put into the disabled mode. So the communication needs to happen one at a time, from the master to the slave. So once the address is a match, communications proceeds between the master and that slave, transmitting and receiving the data. So the transmitter then sends the 8-bit data, the receiver replies to 1 bit of acknowledgement. And hence, when the communication is completed, the master issues the stop condition, which refers to the microcontroller, relaying the information to the slave. So let's understand deeper of how the I2C protocol functions. So below is the basic command sequence, whereby the first step, the master does a bus idle check. It checks for the buses. Is there any slave that wants to communicate with the master? And then there will be the start of communication. And then it's going to check for the unique address of that slave. And then it's going to acknowledge the condition that it has been transmitted to. And then the master to the slave is going to write the operation that is being required, and then the slave is going to read the operation from the slave to the master. So these are just some of the I2C protocols that we had seen in the internship program, specifically from the master, the microcontroller with the RTC. So below we have various bus speeds modes, which are used to communicate with each other from the master to the slave. So for the bus speeds modes, we have the standard mode, the fast mode plus, the high speed mode, and the ultra fast mode. And lastly, we have the RTC, the real-time clock, which refers to the DS1307, which works with the help of the I2C communication, as we had seen earlier, the protocol or the transfer of communication. Hence, it have a serial clock and a serial data pin, which has to be connected to the I2C pins on our PIC microcontroller, which is 18, pin 18, and also pin 23. So in it, we have a pull resistor value of 4.7K or to some 100K, which is used to keep the bus at a high state when it is idle. So what does the real-time clock usually do? So real-time clock usually used to give us the current time of the embedded systems. So for the LCD display, it can be connected to the pins on port D to display the current date and time, which can be used to make a live interaction with the embedded systems and the current world. So for the current world, we have the real-time clock integrated to the LCD, which enables us to read the current value and time, date and time. So the last part, which we were to design the embedded system itself. And for our event, we had to design a car black box project, which is also known as the event data recorder. So this is usually a device that is going to monitor the car driving behavior and performance in terms of speed, events like accident, braking, recording their time when they happen, shifting gears, and etc. So this car black box project, as we had undergone the entire training of using the RTC, of understanding how to design the microcontroller, of understanding how to interface the LCD, how to regulate the potentiometers, and so many other peripherals, is that we can design our own car black box project. And we had designed it as we are going to share it right after this. So with the car black box project, this is a device that is going to monitor the car driving behavior of a person, of the driver that is usually inside, so that it's going to give us the information and help us in the performance of the automobile industry, which can enable us to record events such as accident, collision, braking, and also when does this person shift gears from one to another, and also records the events when they happen, at what time, after how long, which gives us some data that is crucial and can enable us to improve further in our automobile industry. So what are some of the dashboard requirements or the peripherals that were required and the things that were supposed to be in the car black box project? So we had to utilize the CLCD, the character liquid crystal display, which in the crystal display, the LCD, we were supposed to display the event, either if it's a collision, or if it's an on, or it's an off, and then record the time that it is happening, and also have the speed of that car, either ranging from 0 to 99 km per hour or miles per hour. And then in the RTC, we are supposed to integrate the real-time clock to give us the current time that is going to be displayed at the LCD. So we need to interface the RTC to give us the current time. Also, for us to vary the speed, we need to interface the potentiometer, which can be used to vary the speed and have the information displayed at the liquid crystal display at the dashboard. And also we had the next important keypad, the digital keypad, whereby for the digital keypad, we can program it to do a variety of tasks, whereby, like for example, we can shift the 6 gears from neutral to reverse to gear 1 to gear 4. So we can use the digital keypad to shift from one gear to another, up or down. So for us, we program the switch 2 and the switch 3 to either up the gear or down the gear. Also, we used the switch 1 to give us if we have a collision or an on event. And also we are going to use the switch 4 and switch 5 for us to enable to prompt and clearing of password. So if you want to get into the event log and understand what happened to the car black box, we are going to use the switch 4 and the switch 5 to prompt and clear the password, log in, and get the information that we want. And also for us to input the password, we need a code. We need some digits so that the embedded system can look into the password, checks it if it's correct, and then accept the password and give us the information that we want, the event log. So for that to happen, we can prompt switch 1 to switch 4 to input the 4 digits in the order that they are supposed to be, so that when that person inputs the wrong password, it gives a delay of almost 15 minutes. Also, as we had seen, we are going to use the double EEPROM to record the events, which is a temporary storage. A permanent storage is a storage whereby we can use to record the log events and get them whenever we require. So thank you, and let me share my PICSIM lab. The following is my project presentation for the car black blocks project. So let's dive straight away to the PICSIM lab. So as you can see, I have downloaded the PICSIM lab. So as you can see, I have my car black blocks project ready running, but let's see the whole process behind it. So at first, I used the MPLAB X IDE to create the project. So I designed it, I programmed it in the MPLAB X IDE environment, and then later generated the hex file that used it to download it in the PICSIM lab simulating tool so that I can simulate and see how my project is going to look like. So diving straight to the PICSIM lab, I was able to select the board for the Big Genius, and then went on ahead and selected the microcontroller PIC16877A, and then went ahead to the file and load the hex file. So for the hex file, there it is, and then I just said open, and as you can see, it's recording the time. So as we can see, we are having several buttons. Enter password. You're going to use the digital password to enter the password. You can also restart it again to show the events, whereby you can shift the gears on and off. You can vary the speed using the mic potentiometer. Thank you. And thank you once again for the Ematex for this great opportunity in learning embedded systems. Thank you a lot.